Chem 2 Equilibrium Part 3, Le Chatelier's Principle. Please read the definition here. So we will look at several things. We're going to look at change in concentration, change in pressure, change in volume, which kind of go hand in hand, change in temperature. We will evaluate how the reaction will shift depending on changing the concentration, changing the pressure/volume, changing the temperature. So if a chemical system at equilibrium is disturbed by adding a product or reactant, so if I add a product or a reactant, the reaction will shift or proceed in such a way or go in such a direction to consume the part that was added. What that basically means is I want you to kind of think of it as a teeter-totter or a seesaw, right, from your childhood or maybe your parents' childhood. So think of the fulcrum in the center, right, and the fulcrum is the arrow in your reaction. So products are on the right, reactants are on the left. If I add a product, right, if it's sitting there level, which really wouldn't happen in the real world, but we'll pretend as if it's sitting there level, both sides of the teeter-totter seesaw are off the ground, and I add someone on the product side, so that's the right-hand side. Think of it as you're looking straight on from at the fulcrum, standing in the fulcrum position or right near it. And I add someone on the product side, so the right-hand side, then the teeter-totter would go down on that side and go up on the left-hand side. So in order for the reaction to reach equilibrium, it has to shift back to the left. So it's going to shift left to push the teeter-totter back to level. So use the teeter-totter seesaw analogy in your thinking. I wish I could be in front of you right now because I would be able to sort of use my hand or my meter stick to show you that, but you're going to have to get a good visual of thinking of it as a teeter-totter. Okay, here we go. Make sure you've read the slide if you have not done so yet. All right, so here we are, we have a reaction, and remember that we'll be ignoring solids and liquids. We'll only be focused on gaseous or aqueous, aqueous or gaseous. So if you think of this as my teeter-totter, right, and I'm going to make my best attempt to try to mimic what I would be able to do in class with you throughout this process. Okay, so number 1 for 19 says we're adding N2O4. So look at the equation down here. If I add N2O4, okay, it's going to go like this, isn't it, from level. So in order for it to get back to level, I have to push it towards the right, or I have to push down on the right-hand side. So we would say that this is going to shift right. So what I would like to encourage my students to do is draw your teeter-totter line, or what the teeter-totter line result would be. So like this, right? So that's the way the teeter-totter would go. In order for us to get back to level, we have to push it or shift this way. We're pushing towards the right. So it's going to shift right. Try to fix my pen here. Okay, there you go. Okay, so back down to the next example. So I'm going to try to put this back to level. Okay, here we go. So we're going to add NO2. So if I add NO2, it's going to go this way, right? So then I think about my teeter-totter. My would be slanted that way once I added the NO2. In order to fix it, I have to push it this direction. So it's going to shift in the left direction. Okay? So that's when you add something. Think about what happens when you add a person to a teeter-totter or seesaw. Oops. Sorry, this is not easy to do for me. All right, so now we're going to be removing N2O4. So if it's level and someone gets off the side of the teeter-totter, it's going to do this. Agree? Okay, because someone got off that side. So you're going to show the slant. I'm going to show the slant like this. So in order to fix it, I have to push it towards the left. So we would say it shifts left to reach equilibrium. Okay, back to this. We're going to remove NO2. So if it's level, right, equal number of people are on each side, kids on each side, and a kid gets off the side because they're being removed, then this side is going to go up. So it's going to look like this. It's going to shift like that, right? Or it's going to be slanted like that, I apologize. And for it to push it backwards, we're going to have to push towards the right. So it's going to shift right. Okay. Okay, now I'm going to look at this one down here. So give me a second here. Let's go ahead and copy this so I can make this sort of my teeter-totter seesaw. Here we go. Give my space self-similar. Okay, so looking at 20, number 1, adding CO. So CO, if I add CO, it's going to move like this, right? So then it's going to slant this direction, and I'm going to have to push it back towards the left in order to reach equilibrium. Okay. All right. Let's get this back to level, or close as I can get it with my mouse. Okay, adding or removing carbon. So here's carbon. Now I haven't pointed this out before because if you notice on this one up here, everything was in the gaseous phase, so everything would affect the shift. Carbon and As4O6 are solids. So nothing, it will not affect the shift because we don't account for them because they're solids, or liquids. In this case, they're solids. So you would say no change here. Or no effect, however you want to write it. No change is how I usually refer to it. Okay, now part 3, we're going to remove gaseous ASO4. So if it's level and we're going to remove someone from this side of the teeter-totter, it's going to go like this. So we're going to show the slant going like this. So we're going to have to push this way. So we're going to have to push to the right to get it back to equilibrium. Okay, going on. So that's adding or removing. That's stuff that we just talked about would be if you're changing the concentration. So you're increasing or decreasing. So adding more of something would increase its concentration. Okay, changes in pressure. So this is an important piece to know because changing in pressure also changes the volume. Remember that pressure and volume are inversely related, meaning if you compress a gas, its volume is going to go down, but its pressure goes up, right? Think about holding your thumb on the end of a syringe without a needle, of course. And if you push the plunger down, it's really hard to push it. It's easy at first, and then it gets harder because you're increasing the pressure while you're decreasing the volume. Okay, so the pressure goes up as you decrease the volume. So let that be a thought. So we're going to talk, you need to understand the terms here for this, like compressed, right? You need to know that when you compress it, your pressure goes up, right? And your volume is going to go down. So you just have to know that they're oppositely related. That's just something you should know from ideal gas laws and from gas laws. And it says that increasing the pressure, the shift is in the direction that decreases the total number of moles of gas. So when you increase pressure, you're going to go to the smallest side with moles of gas. So you're going to look, you're going to count on the left side and the right side of the reaction the moles of gas, and you're going to shift when pressure goes up. You're going to go to the smallest number of moles. All right. Inversely, when you expand something, right? So increase volume, your pressure is going to go down. Okay. And you're going to shift towards the side that has the greater number of moles. So you're going to say largest or greater number of moles of gas. So make sure they're gas. Remember, for the most part, this whole unit, we're ignoring anything that's in the solid or liquid phase. So let's do some practice on that next. Okay, you really have to think about those relationships when you go through this. You kind of have to be talking about them in your head as you're working through this. So that's really important to do that piece. Okay, so we're talking about, and I honestly think you will do much better if you just do some writing down or at least thinking, right, on scratch paper or something. So pressure decreases. So we know if pressure goes down, that means volume went up because they're inversely related. And we know, so let me go back for just a moment, something that I meant to point out and I did. So volume does the same thing in a sense that the way we shift. So if your volume decreases, so getting smaller, smallest number of moles. Volume goes up, you're going to look to the side with the greatest number of moles of gas. So you can think of the fact that pressure and volume are inversely related, oppositely related. Pressure and small moles of gas, or let me say that better. Pressure and moles of gas are inversely related, and volume and moles of gas are directly related. So whatever volume does, if volume goes down, then you're going to look to the smallest number of moles. That's which way it's going to shift. If your volume goes up, you're going to look to the side, shift towards the side that has the largest number of moles. And then pressure would be the opposite. So remember, pressure is the opposite of everything else. So here we talked about pressure going down, which we know then volume must be going up. And so we talked about the fact that we are going to look for, so if it's pressure and we know volume, so we're going to look for the greatest number or increase, I like to say it that way just to keep the arrows the same, number of moles. Okay, so what does that mean? So we split the reaction. We say there's a total of 2 moles of gas on this side and 3 on this side. Okay, so which side has the greatest number of moles because the volume went up? It's going to be, we're going to have to shift to the right. Remember, we're always starting at the arrow, and we're going to either go to the right or to the left starting at the arrow. Okay, again, we shifted right because this has greatest number of moles. Okay, increasing pressure, so I think about pressure going up, which means volume goes down because they're inversely related. So I'm going to shift to the least number of moles because we know that volume and number of moles are directly related. All of these can count because all of them are in the gaseous phase, just like all of these were in the gaseous phase, so I have to count them. There's 2 here and 2 here, so you'd say no change or no effect. Cannot be determined, those words work also. We're going to ignore this because it's a solid. So that might be the first thing you want to do on these is cross off anything that's a solid because they will be ignored. So we're decreasing pressure, so pressure is going down, which means volume's going up, so we're looking for the greatest number of moles. All right, so this has 2 and this has 1, so that's going to have to shift to the right because the right-hand side has the greatest number of moles. Okay, change in temperature. Change in temperature is a little different than the other two, but we can get through this. Let me walk you through. An increase in temperature causes an endothermic reaction to occur, a decrease in temperature. So if I'm going to increase temperature, then it's endo. If you see a decrease in temperature, then it's exo. Okay. We have to also consider the effect of the equilibrium constant. Nothing except for temperature has an impact on how your equilibrium, your K value changes, your Kp value changes, whatever. But temperature does. So we're going to look at that right here. It says, unlike changes in concentration or pressure, changes in temperature cause a change in the value of the K. And the value of the K changes, then the results of your reaction are going to change, or the answers are the same. So we're going to look at it in terms of endo and exothermic. So if it's exothermic, then K is going to decrease as temperature increases. Okay, so if it's endothermic, I'll do the last piece I was about to say in a moment. If it's endothermic, then when K increases, temperature is going to also increase. So you first have to establish if it's exo or endo, right? And then, pardon me, first have to establish if it's exo or endo. And we'll talk about how you know that. Remember that if it's delta H is negative, it's exo. If delta H is positive, it's endo. Okay, so if it's exothermic, right, then they're opposite, meaning K and T do the opposite. So if you know your temperature increased and you know it's exothermic, you know K decreased. If you know it's endothermic and you know temperature increased, you know K also increases. So if it's thermic, then K and T are opposite of each other. So one goes up, the other goes down, and vice versa. If it's endothermic, then K and T will do the same thing. As one increases, the other will increase. Let's practice. Okay, remember that you will not even care about K unless you're dealing with temperature. So if I ask you about K for pressure or concentration, you would say no change. But if it's temperature, you have to evaluate K. So increase in temperature would cause a, okay, so we look at this chemical equation. I gave you a value of delta H. Remember that if it's a delta H is positive, it's endo. So that means that your temperature, so to speak, and this is just a rough way of thinking about an analogy, your temperature is over here. Because remember, exothermic means exiting. So endothermic means entering. So T is here on this side, on the reactant side. So if it's endothermic, a positive delta H, you're going to have temperature as kind of like part of your balanced equation, just to be able to see the teeter-totter piece, right? So if I increase the temperature, so I'm thinking about this one right here, right? So my temperature is level, or my balanced equation is level. I have temperature over here, right? And I increase the temperature, it's going to shift this way. Think of temperature now just as another person getting on and off the teeter-totter, okay? So it's going to have to shift this direction to reach equilibrium. So it's going to have to shift right to get back to equilibrium. Okay, and then if we can look at this one, so I'm going to label this as number 1, and this is going to be number 2. Okay, so now looking at number 2, think of it as level, right? And we still know that temperature is endo, so it's on this side. If I can put my fulcrum, that was a horrible triangle, there, right? And I'm going to decrease temperature. It's going to do this, isn't it? Because my temperature's here, and some of the temperature got off the teeter-totter, so it's going to have to shift to the left, in this case, to reach equilibrium. Okay. Now, let's talk about how does K change. So we know this is endo. When we know endo, they do the same, meaning T and K go up and down together, okay, or up together or down together. So I'm looking here, and I know that it's endo, and I know increase in K, so I know increase in temperature, so that I know it's also increase in K. Because it's endo, I know temperature decreased, right? So K will have to go down. So they are going to do the same thing if it's endothermic. All right, last example. So now we're looking at something being exothermic. So we're going to think about T being here. Why is it exothermic? Negative delta H. So if I think of number 3 being level, as level as I can draw, temperature's on this side if I think about my teeter-totter, right? And if I increase temperature, it's going to do this, isn't it? So I'm going to have to shift to the left to get it back to equilibrium. If I think about number 4, we'll pretend that's level. And I know my temperature's over here, right, to start out. And I decrease temperature, it's going to go like this because something got off, right, the teeter-totter. So this side goes up. I'm going to have to shift to the right. Okay, to get back level. Okay, so now we're looking at this being exo, right? We know this is exo. So we know that if it's exo, whatever T does, K is going to be opposite. Exo is opposite. So therefore we know K is going to decrease because T had increased, because they're opposite, because it's exo. And then for number 4, we know that K is going to increase because temperature decreased. Okay, that is the conclusion of these notes. You will have some practice and assessment most likely. So good luck. Check in with me as you need to.